Okay, let's dive right into this explainer. Today we're popping the hood on something truly fascinating, the back end of a cutting-edge AI medical system. We're going to decode exactly how a modern, agentic, RAG-based medical chatbot actually works. If you've ever found yourself wondering how artificial intelligence can safely handle really complex health questions without, just completely guessing, well, you are definitely in the right place. Usually the whole process kicks off with a really relatable question. Something like, hey, I'm on this medication and suddenly I've got this weird new symptom. What do I do? Now, obviously, this is an incredibly high-stakes query. If a standard AI model hallucinated an answer here or just made a wild guess, the consequences could literally be life-threatening. So how does an advanced system handle this accurately, safely, and most importantly, transparently? To answer that, we're going to follow the journey of a query. We'll start by meeting the system, then move to phase 1, looking at the input and agents. After that, we'll hit phase 2, breaking down the RAG tech stack, and finally wrap up with phase 3, covering translation and delivery.
All right, section 1. Let's meet the system.
Now, what really separates this from your everyday run-of-the-mill chatbot is this concept of agentic RAG. As you probably know, RAG stands for Retrieval Augmented Generation. Instead of relying on an AI's potentially spotty built-in memory, RAG forces the AI to actively fetch and fact-check data from external authoritative sources. But it's the agentic part that makes this a real game-changer. It acts way less like a single computer program and a lot more like a board of specialized doctors, all consulting an ultra-fast medical librarian. They autonomously decide when they need more information, when to ask you clarifying questions, and, crucially, when it's time to call in human help.
Moving on to Section 2, Phase 1, Input and Agents. The exact second the system receives a query, it kicks off this incredibly sophisticated triage phase. Human language is, well, it's messy, right? We don't speak in neat little data points. So a natural language processing, or NLP pipeline, instantly scans the text to yank out the concrete medical entities. Based on what it finds, it wakes up specialized agents. It's basically categorizing the user's urgency level and medical complexity in just a matter of milliseconds. A lot of this initial heavy lifting relies on an advanced NLP technology called SPACY. It's essentially the translator, turning human worry into precise, trackable medical data. So, if a user types something like, "My head is pounding and I feel dizzy after taking my blood pressure pill," the SPACY pipeline instantly normalizes that. It tags the exact symptoms, it flags the medication category, and figures out the temporal context, like how long this has actually been happening. It's literally transforming raw emotion into structured clinical data.
And this perfectly illustrates that multi-agent framework we talked about earlier. Think of it like a specialized hospital staff coordinating to manage a patient. Once that text is processed, these different agents spring into action. You've got the symptom analysis agent categorizing what you're feeling and checking risk factors. The medication information agent is busy normalizing drug names and checking for interactions. And all the while, the emergency assessment agent is constantly watching the data, figuring out if this is a critical situation that demands immediate human intervention.
All right, Section 3, let's dig into Phase 2, the RAG tech stack. Let's break down the actual back-end architecture, making all of this happen. LangChain is basically the nervous system here. It orchestrates the workflows between all those specialized agents and manages the retrieval pipelines. Then you have ChromaDB and Pinecone acting as the deep memory. These are vector databases storing millions of medical concepts in a way the AI can instantly search by meaning, not just exact keywords. OpenAI's GPT-4 serves as the brain for text generation and reasoning. And lastly, Redis provides intelligent caching, remembering past queries so it can optimize performance and really speed up those response times.
But here's the thing, a brain and a memory are really only as good as the information they hold, right? So this system taps into a massive, dynamically updated library. By integrating directly with the PubMed API, major clinical practice guidelines, and comprehensive drug interaction databases, it ensures the AI relies strictly on peer-reviewed science. No guessing, no making things up. If a medical recommendation changes out in the real world, the system's dynamic knowledge base is instantly updated to reflect that.
Now, to find the exact right piece of information in that massive library, the system uses what's called an ensemble retrieval strategy. It doesn't just search using one method. It uses vector similarity to find concepts that mean the exact same thing, keyword-based BM25 retrieval for precise terminology matches, and semantic matching to really grasp the broader context. By running all of these search strategies simultaneously, it ensures absolutely no critical medical context slips through the cracks.
Once all that data is retrieved, it obviously has to be filtered. And this is a crucial point, the medical relevance scoring mechanism. The system rigorously ranks the retrieved data by domain expertise, publication recency, and the actual level of clinical evidence. This scoring is the ultimate safeguard. It guarantees that a critical, scientifically backed drug interaction warning gets pushed right to the very top of the AI's priority list rather than getting buried under some obscure 10-year-old research paper.
Which brings us to Section 4, Phase 3, Translation and Delivery.
Here is where you see the incredible translation power of the system totally shine. It takes dense PubMed clinical jargon, stuff that would completely overwhelm your average patient, and transforms it into a clear, patient-friendly explanation, all while maintaining absolute medical accuracy. And importantly, it provides crystal clear source citations. The user can see exactly where that medical evidence came from, which builds a ton of trust.
But wait, the interaction doesn't just stop with a simple answer. The system actually generates intelligent follow-up questions. Based on the medical best practices and clinical guidelines it just pulled, it actively looks for information gaps. It might ask, hey, what exact dosage did you take? Or do you have a family history of this specific condition? The AI isn't just a passive search engine here. It's an active participant gathering vital context to really refine its medical assessment.
All of this builds into the ultimate patient safety net through continuous escalation monitoring. The system literally never stops watching the conversation state. As you answer those follow-up questions, the agents are constantly tracking for complex conditions, flagging severe drug interactions, and identifying any emergency symptoms. The second it detects a trigger that requires immediate human medical professionals, it executes a seamless escalation protocol, handing over a highly detailed comprehensive medical summary directly to a human doctor.
And that brings us to the end of the query's journey, leaving us with a pretty provocative final thought. We've seen how this system processes messy natural language, pulls from peer-reviewed databases in milliseconds, and synthesizes it all safely. So what happens when personalized, highly accurate medical triage, backed by the entire history of medical literature, is instantly accessible right in everyone's pocket? It's a fascinating future, one that perfectly blends AI efficiency with that absolutely essential human medical oversight. Thanks for hanging out with me for this explainer. I'll catch you next time.